Hello and welcome to our Wednesday webinar from the International Centre for Sustainable Carbon. My name is Benedicta and I'm part of the communications team here. Our monthly webinars are based on our technical reports, which are available from our website, sustainable-carbon.org. Please type any questions you have in the questions box as we go along, and we'll answer them at the end of this webinar. The subject for today's webinar is Operational Flexibility of Coal Power Plants and Carbon Capture, presented by Dr. Qian Zhu. Over to you, Qian.
Thank you, Benedicta. Hello, everyone, and thanks for tuning into today's webinar. As you may know that the global coal power generation capacity has been expanding since the Paris Agreement was reached in 2015. Coal will remain a critical source for electricity production until 2050 or even beyond, especially in most parts of Southeast Asia and parts of Africa. Therefore, decarbonising coal power generation is vital to meet global climate goals. Carbon capture is central to the least cost pathways to net zero emissions. Today, I will look at the operational flexibility of coal power plants equipped with carbon capture systems. Right, here is today's outline. First, I will briefly review the existing technologies for improving the operational flexibility of the conventional coal power plants with a few case studies. I will then look at the existing and the emerging carbon capture technologies and their applications on coal power plant, and explore measures to flexibilize the operation of CO2 capture systems. Trade-off of flexible operation of CO2 capture plants will be discussed, and finally, the key messages for you to take home. Now let's begin with increased flexibility of coal power plants. With increasing share of variable renewable power in the electricity system, coal power plants are increasingly required to operate flexibly with wider load range, faster ramping, and frequent starts to balance the grid. Technologies and measures exist, and the options are extensive to enhance the flexibility of conventional coal power plants. From the perspective of optimizing the combustion system, it is possible to achieve higher flexibility through changes to mill size, the number of mills in operation, optimized fuel and combustion air ratio and distribution, and better burner designs and arrangement. Further, measures such as reliable coal ignition and flame detection, installing a hot gas generator, and or indirect firing, and optimizing auxiliary systems that can lower minimum load, increase ramp rates, and allow faster startup of coal power plants. For water steam cycle and turbine systems, engineering retrofit to enable steam bypass certain processes, such as feed water heater, condensate and economizer, installing thermal energy storage, and the feed water repowering can optimize the water steam cycle for power generation, leading to increased ramp rate, optimized unit startup and shutdown, expanded load range, as well as higher efficiency. A similar design of SIG-Watt components by using high-grade materials, sliding pressure operation mode, and the improved operation procedures will also enhance flexibility significantly. The instrumentation and control system, or I&C system, is the link joining all aspects important for the efficient plant operation, and can be the most cost-effective way to improve plant performance. In most cases, fine-tuning the existing control system can improve plant flexibility and efficiency. However, for power plants using lower level of I&C systems, digitalization provides enabling technologies for improving flexibility, performance, and efficiency, as well as reduced costs. When the operation of coal power plant changes from baseload norm to flexible or cycling mode, the plant operating procedures need to be revised. Further, change to certain plant operational practices with proper operator training can unlock latent flexibility at existing plants. There have been many reports of successful upgrading of existing power plants, coal power plants, using some of the measures I just mentioned to achieve increased flexibility and improved efficiency. For example, a hard coal-fired combined heat and power plant in Denmark has a generating capacity of 410 megawatts in condensing mode, or 350 megawatts with steam offtake of 500 megajoules per second simultaneously for district heating. When commissioned in 1922, this unit was already designed with high degree of flexibility. Since commissioning, 3 measures, as listed in here, have been taken to further enhance its flexible operation. By installing heat storage tank and shutting off low-pressure preheaters, net power output during peak time and the maximum heat output were increased. By fine-tuning control loops for feed water supply and configuring existing hardware, the minimum load were reduced as shown in this figure. The area covered by blue lines represents the originally designed power and heat output, and the area covered by both blue and green lines exhibits the possible power and heat output after the improvement, and you can see it has been increased. A lignite-fired power generating unit in Germany that was built in 1975 for baseload operation had a capacity of 600 megawatts with a minimum load of 73% or 440 megawatts. It was modernized around 2010 by plant components engineering, including the boiler and the condenser, and upgrading the I&C system to enable flexible operation. A new robust state space unit control system was installed, and all the subordinated controllers were optimized. After the modernization, the minimum load of the unit decreased from 440 to 270 megawatts, and the run rate increased from 5 megawatts per minute to 15 megawatts per minute. This unit was retired at the end of March 2024 in accordance with the German government's Coal Phase-Out Act. The plant operation can become more flexible by simple and inexpensive procedural and operational changes. As an example, operators at a US power plant with two 1,300 megawatts units had to operate each unit at or above 800 megawatts. Operating any of the unit below 800 megawatts was restricted because it would be below the optimal speed range of the two boiler feedwater pumps in operation. By changing the operating procedure and taking one pump out of service, which was against the standard operating procedure, the operator were able to operate each unit at a new minimum load of 550 megawatts. As a result, this procedural change has become standard for turndowns, and the utility could take the additional 500 megawatts off the grid without having to shut down any units. This saved the utility about $2 million per year in avoided startup costs. Due to the limited time, I'm unable to discuss the technologies in detail, but for those of you who are interested, please refer to my report, which is expected to be published in May, that's next month. Or you can go to our website for more information. Our center has published several reports on this topic. Now let's move on to carbon capture technology. Amine-based absorption is a well-established technology for CO2 capture, but its application in power sector is relatively new. Extensive R&D to expand existing technologies to post-combustion capture, in short, PCC, of CO2, from coal-fired power plants have led to several successful pilot and commercial-scale demonstrations of amine solvent-based PCC systems. Amine-based PCC systems are now commercially available from several suppliers. Any near-term application of CCUS on coal-fired power plants will be most likely to use amine-based PCC technology. Other technologies such as solid solvent adsorption process and the membrane separation process are under development as well and are being demonstrated or to be demonstrated at large scale at large pilot scale. Some commercial scale amine-based PCC systems have been or are being tested and demonstrated on existing coal power generating units, such as the well-known 150 megawatts Boundary Dam CCS project in Canada and the 240 megawatts Petronova CCS project in the USA. Recently, several large-scale amine solvent PCC demonstration facilities with capacity of up to 1.5 million tons CO2 per year have been or is being installed at coal-fired power plants in China, as shown in this slide. Tests of these demonstration projects show many similarities to how the developers were able to overcome the initial technical and operational challenges. As typical of a first ever demonstration of a new technology at full scale, the capture systems at Boundary Dam and Petronova experienced some technical and operational issues as one would expect. However, the major issues encountered in the early operations were found to be within the technical and engineering capabilities and were successfully resolved. Figures in this slide shows the performance of the PCC plant at the Boundary Dam and the Petronova and how they have improved over time. The technology has continued to evolve, and the performance and the reliability of the PCC systems can be further improved and the cost reduced with technology advances and optimized operation and maintenance procedures by learning from this demonstration project. It is clear that amine-based CO2 capture technology works on coal power generation units at commercial scale and can achieve CO2 capture efficiency of above 95%. Therefore, CCUS can be used to decarbonize coal power generation. For integrated power plants and the PCC, the capture system must follow the operational regime of the host plant and achieve high level of CO2 capture at the lowest cost. Therefore, capture plants need to be flexible enough to deal with the load variation of the host power plant. There is ongoing work on operational flexibility of PCC systems and some measures to flexibilize the operation of PCC plants have been proposed and investigated and will be discussed next. One is the segregated solvent inventory with solvent storage. In this configuration, the lean and the rich solvent can be circulated in two separate short loops when needed, as shown in the figure on the left here. The lean and the rich solvent storage tank provide adequate quantity of lean solvent in the system prior to the startup and sufficient capacity to store rich solvent until normal regeneration operation is reached. With this arrangement, the absorber can start to capture CO2 as soon as the boiler is fired up. The rich solvent built up during the startup is worked off after regenerated solvent supply is established. Once regeneration of any solvent is established, the circulation is started by transitioning from segregated inventory to circulating inventory, that is, normal operation. Consequently, the startup of the PCC process is reduced, while the high CO2 capture efficiency during the startup is ensured. Another measure is to install a solvent storage system. With solvent storage, the energy and the capacity penalty due to the operation of PCC can be shifted in time by storing rich solvent and regenerating it at a later time. When power demand rises, the rich solvent from the absorber is sent to a rich solvent storage tank instead of the dissolver. The CO2 capture in the absorber operates at full capacity by drawing the lean solvent from lean solvent storage tank. Meanwhile, the steam for solvent regeneration is diverted to steam turbine to boost net power output. When power demand decreases, the absorber and the dissolver return to their normal operation mode and regenerate the extra amount of rich solvent to replenish the lean solvent tank, which leads to a lower net power output. The maximum duration of the transition operation mode of the PCC plant depends on the size of the solvent storage tank. By careful calculation of the storage tank size, the design of solvent storage can be incorporated into that of a segregated solvent inventory for a flexible PCC system. During power plant startup sequence, steam is produced at various pressures that cannot be admitted to the steam turbine. This steam is typically depressurized and dumped into the main condenser until steam quality is reached and the warming of the steam turbine is completed. This waste early steam can be used in dissolver reboiler for equipment preheating and the solvent regeneration to accelerate the startup sequence of the PCC process. Similarly, substantial waste steam is available during the shutdown sequence, and this waste-less steam could be used for further solvent regeneration, as shown in this slide. This approach can reduce startup time of the PCC and increase the average capture rate of a given starting and shutdown sequence. Combining this technology with solvent storage can improve energy and the CO2 capture efficiency and hence lower the cost. Installing a thermal energy storage system can provide instant thermal energy to preheat the dissolver reboiler during startup. Also, during peak demand, the stored thermal energy can be used for solvent regeneration and send all the steam from steam generator to steam turbine to increase the night power to the grid. The heat storage can be topped up during low load operation period and or prior to the power plant shutdown, and continue the regeneration operation in the dissolving boiler to treat residual flue gas. Stable operation of PCC at lower load can be achieved by using multiple smaller equipment such as the absorber, dissolver, and the CO2 compressors. The flexibility of PCC systems can also be enhanced by using advanced I&C systems. Flexible operation of PCC involves trade-off between performance, efficiency, and the cost. Adopting flexible PCC system at a power plant will increase capital and operating costs, reduce net power output, resulting in the increase in generation cost. The CO2 removal efficiency of a PCC plant will be lower during flexible operations compared to that during steady-state operation. It's important that PCC plants should be operated under steady-state conditions as far as possible to maintain optimal performance and the CO2 capture efficiency. The frequent and the rapid ramping must be avoided due to its detrimental effect on the chemistry. The load change operation of power plant equipped with PCC can be enabled by installing solvent storage or thermal energy storage system, which temporarily decouples the PCC operation from power generation. This allows PCC to operate as normal while the power generator is ramping up or down, minimizing any negative impacts on CO2 capture performance during load changes. On the other hand, adopting a flexible PCC system may have some economic benefits by improving the plant's position in the merit order for dispatch and increasing revenue. Therefore, the design of a PCC system for power plant should be optimized to balance between flexibility, costs, and minimizing CO2 emissions. So this leads to the key messages from this study. The role of coal power in energy transition will not disappear, but rather with existing and innovative technologies, it can and will evolve into a more dynamic and a responsive function. CO2 capture technology on coal power plants works at commercial scale and can achieve CO2 capture efficiency of above 95%. Therefore, CCUS can be used to decarbonize coal power generation. PCC-equipped coal power plants can operate flexibly, providing fast responding backup capacity. They can have an important role in modern power systems to provide low emission flexibility, capacity, and other vital system services to the grid. That's the end of my presentation today. And thank you very much for your time. See if there are any questions. Oh, there are no questions here. Oh, there is one. So what the carbon capture processes are used in the Chinese demonstration coal power plant? The vast majority of the carbon capture process used in China are the amine solvent-based technology. Last year, there was a solid solvent adsorption process being commissioned. It was a pilot scale demonstration project. There hasn't been any information available about the test results, but for the demo project listed in my earlier slides, those projects are all using the amine solvent-based PCC process developed by different developers. So they vary in the process design and the solvent, the chemistry, but it's all amine-based PCC system. So I think this is it. No more questions.
Okay, thank you very much, Qian. And all that's left for me to say is the slides from this webinar will be available to download from our webinar page on the website shortly. And as you already said, Qian, your report will be published on our website in May. Thank you all for joining us today, and goodbye.